Hello everyone. Today, I have the pleasure of presenting our research paper on behalf of my co-authors. The paper is titled, Learning Low-Rank Latent Spaces with Simple Deterministic Autoencoders, Theoretical and Empirical Insights. In the upcoming slides, I'll provide a brief overview of autoencoders and then delve into the technical side of our novel model. A simple autoencoder maps data from the data space to the latent space and then reconstructs it back. Typically, the latent space is a low-dimensional vector space, with dimensions commonly set at 256, 512, or 1024 in literature. Let's take the example of a 1024-dimensional latent space. The 1024-dimensional latent vector actually occupies a smaller dimensional subspace within this expansive 1024-dimensional vector space. As a result, our model is designed to learn an even lower dimensional latent space where the latent vector actually lies. This approach is fundamental to achieving a more accurate representation of the data. To facilitate the learning of a rank-deficient latent space, a linear layer is strategically positioned between the encoder and the decoder components of the autoencoder. This layer can be conceptualized as a real square matrix, serving the purpose of projecting data onto a low-rank latent space. The process of learning this low-rank latent space involves simultaneously minimizing the nuclear norm of this matrix and the reconstruction loss of the autoencoder. Hence, the autoencoder adaptively acquires the ability to represent data within a rank-deficient latent space efficiently. To provide empirical evidence demonstrating the effectiveness of our model in learning a superior latent space than other baselines, we have conducted a series of experiments. These experiments will be detailed in the upcoming slides. To show that our model learns a better latent space, we conduct linear interpolation in the latent space and observe data space transitions for the MNIST dataset. In Figure 3, we compare these transitions with those from a baseline autoencoder, a variational autoencoder, and an implicit rank minimizing autoencoder. It's evident that our model yields smoother transitions compared to these other models. In Figure 4, we examine how quickly our model reduces the dimensionality of the latent space. We find that a simple autoencoder tends to utilize nearly the entire latent space, whereas the implicit rank minimizing autoencoder drastically reduces the dimensionality. Our model, in contrast, achieves a more gradual and smoother reduction in dimensionality. These experiments confirms that our model learns a better representation of data than baselines. One method to demonstrate a model's effectiveness in learning a better latent space is by its ability to generate high-quality images. We trained a simple autoencoder, a variational autoencoder, VAE, an implicit rank minimizing autoencoder, and our model on the CelebA dataset. After training, we fitted a 4-component GMM to the latent space and randomly sampled latent vectors. These vectors were then passed through the decoder to generate images. Figure 4 clearly shows that our model produces higher quality images compared to the baseline models. While the VAE tends to generate blurry images due to its probabilistic nature, our model is able to create sharper and more defined images. We evaluated our model's generative capabilities against other top deterministic autoencoders, including the Wasserstein autoencoder, WAE, and the regularized autoencoder, RAE. To assess the quality of the generated images, we used the Frechet inception distance, FID, score. Our findings show that our model outperforms a simple AIR, VAE, IRMAE, WAE, and RAE on the MNIST dataset, ranking second on the CelebA dataset. Additionally, when comparing our model with various generative adversarial network (GAN) models, we observed that it achieves comparable FID scores. We conducted a downstream classification task on the MNIST dataset, where latent vectors from trained autoencoder, AE, variational autoencoder, VAE, and our model were used as inputs for training a simple linear classifier. Our findings reveal that, thanks to the low rank constraint, our model outperforms the AIR and VAE baselines in low data regime, while still delivering similar performance on the full dataset. We provide robust mathematical justification for this enhanced downstream classification performance in Theorem 2 in a later slide. Now, we will move on to the theoretical analysis of our model. We include convergence analysis and also demonstrate that even if latent spaces are high-dimensional, say 2048-dimensional, our model does not suffer from the curse of dimensionality. We establish that our learning algorithm, when used with the Adam optimizer, converges at a rate of big OT to the power minus 0.25. While this rate is somewhat slower compared to SGD, improving it presents an opportunity for future work. In this slide, we address the issue of the curse of dimensionality. Even though latent spaces are low-dimensional, spaces of order 2048 and above are often affected by this curse. We demonstrate that our model overcomes the curse of dimensionality. The inclusion of a low-rank regularizer ensures that the min-max distance ratio in the latent space is always lower bounded by a real positive constant. This constant is dependent on the penalty parameter lambda and the training data. This aspect allows the latent vectors more room to be effectively distinguished and accurately classified, even in scenarios with limited data. Intuitively, a higher penalty leads to a lower rank of the latent space. We present a proposition to support this and also empirically demonstrate that both very low rank and full-dimensional latent spaces fail to provide the desired representation. Therefore, it's essential to adjust the lambda parameter appropriately to achieve an optimal representation. In summary, our findings indicate that integrating a low-rank constraint into a standard autoencoder results in a more effective latent representation of data. This enhanced model not only generates higher quality images from latent spaces but also shows improved performance in downstream tasks. Moreover, it provides robust mathematical guarantees that reinforce the empirical evidence we have observed. Thank you and have a great day ahead.